Hello everyone, today we will be learning about linked list. This is the content that I will be covering in this video. Let's begin with why do we require linked list. So we know that array is a very much common and convenient dataset that we use in C++. However, during initialization, an array requires to be given a size, and thus this becomes a static dataset. And this it is not always convenient to use an array because it is static. What the static refer to is the size cannot be altered once the size is initialized or given. Thus, in a case where a user is supposed to be giving a data set, the size can be either insufficient or can be unnecessarily very large. So thus in this scenario we often try to use a linked list. Because why is this it is so because a linked list is a dynamically sized data set. So this refers to the fact that a linked list is a size initially of 5. It can later go on and change itself to be 7 and can also become of the size 10. Thus it is according to the user's input. So we have gone through this. What is a linked list? So going ahead to the what section. A linked list is, you can see, a data set that has a data, say 3. It also has a pointer towards the next link or the next data that is going to be stored, say 8. This further on goes and forms another link with the next data, say 5. And let's say this is the last data that we are supposed to store, so this has a null pointer, and we are very sure about this, that null refers to nothing, that is void, very much similar to the word or the fact of 0. In C++, we often use null or 0. And something very important, crucial that I have missed over here is a pointer that is called first, or also known as head of a linked list. This is a pointer that always points or stores the value of the data that is going to begin the linked list. Say this is 200, then the first or the head of the linked list is supposed to store 200. Say this is 310, this is supposed to store 310. Something I forgot to mention is in linked list the data set, the datas are not continuous in the heap, they are stored randomly. This can be, say, 200, this can be 400, and this can be 470. Whereas in an array we know that the data, say, of size 5, so it is 200, 204, 208. Considering all our integers, thus we have an increment of 4 every time, and the address of the array is the address of the first element, that is the 0th indexed element. So we are also done with what. Now let's begin with the definition of, or the method of defining a node, or a how do I say, linked list in C++. So this is known as a node. So a node is a data type that stores a data and also has a pointer pointing to the next data. This is what is a node. And there is no certain data set that is, or a data type that straight up defines a node, that is a data that stores the data as well as a pointer. So we are supposed to have our own data type that is going to be a user defined data type, and we can accomplish this task by the help of struct that is used in the C language, whereas in C++ the struct equivalent is a class, the concept of hoops. However, a notable difference amongst these is this by default has everything public, whereas in class everything by default is private, and thus we are going to be using struct because C++ also supports struct, unlike C, which is unable to support class. So beginning with the definition of node. So this is how we write a user defined data type, that is struct. So we name our data type as node. This is int data, the first step. So say this is our node, this is for the data type. This can be of any data type. It can be float, it can be a double, it can be int. That depends on what we would like. Next, moving on, this is next. This is going to be the name of our pointer, let's say, that is going to be pointing to our next node. Thus this pointer is named as struct node pointer. As you can see, this is using this user data defined data set itself, data type in itself, and thus cases like these are known as self-referential data types or data. So here we can see an example of self-referential data that is using the same data type in itself. So this is how we define a node, and what you see next right here is what we are creating a node. This is creation of a node. So we give the node a name and we assign it a new value. So this is going to be some water. Now say this is our node creation. We would like to have a data, say a data of 7. So we write the name of the node, that is P in this example. Then we make use of an arrow, that is an hyphen with the less than sign or the greater than sign. Then we write the data. This equals whatever data we would like to enter. Here 7, and for next, here whatever is our data, the pointer that is going to be assigning to the new link. Say in this example we want it to be of null. Thus we write P next. You can write 0 or null. I would like to prefer using 0 here. So that is how we create a node. So this is done. Now we'll go ahead and look into key conditions. So beginning with our key conditions, as you can see, we have written down struct node star p star q. This refers to two pointers named p and q being created. Let's say our p is our head and it is already pointing to a linked list. Say this is our example with data 8 3. Say this is of address 190. So since this is next, it is going to be storing this address, so it is going to be storing 210, and this is our null pointer. So in this example 190 is going to be stored in p because that is the address. Now p equals q, or rather I should have written it the other way, q equals p. Writing this clearly means that q is going to take whatever value is present in p. So this implies q becomes 190 in this case. Now let's say we write q equals p next. What this refers to is q will take the value of the next, will take the value of next in p, and if you look closely over here, next is the pointer that is pointing to the address of the data of the next node in the linked chain, thus the value 3. So this implies q is going to store the address of the next node in the linked list. So our next condition in the key conditions is p being p next. Sorry, p equals p next. What this case does is this essentially updates the value of p to p next. This is going to be storing the value this stores the value of the address of the next linked list. However, p is an integer, thus it will change its value. It is a pointer, thus it goes from 190 in this case to 210. This is also going to be extremely important since it helps us traverse in a linked list, which I will be covering next. Then we can mark this as done. So now let's begin with a traversal in a linked list. So let's say, for example, this is our linked list where the first stores an address of 210, that is the address of the value of the first node in the linked list, and the linked list then further the next goes on to the data of 3, and then that is the tail of our linked list. So it is the first step in traversal of a linked list is creating a temporary or another pointer that is equal to our first or head of the link. It is always our primary and most crucial step of making another pointer that is equivalent to our head of the linked list. A next step is always recalling that we have to update our pointer p. The pointer p is going to get changed as we go further ahead in our traversal. So for example, I will make this a bit longer so I get a bit more explanation in here for better clarity for you all. So let's say the next value is 5 and has 310. So this stores 310 and this is our null pointer. So our task is to begin with here. Since it is equal to first begins here, then our task is to update p to come over here and then here, and realization we get over here is we will have to require a loop, since a loop helps our task to go forward repeatedly without us having to call the statement again and again. However, what we realize here is a for loop is not possible because we do not know the size of a linked list. Thus, we require a while loop. However, the while loop requires a condition, and a condition we are very certain is that the end. Once we reach the null pointer, it is surely the end of our loop, and thus we will have the condition of p not equal to null or 0. That is whatever you would like to state. While p is not equal to 0, see out p. So this helps us print the data, whereas if you say you have an integer count equals 0, see you have now count plus plus. So every time it traverses through the linked list or every time it goes through a new node, the count increases, and thus that also helps us in counting the number of elements in the linked list. Now our next and very crucial step is to update the value of p, and thus the updation will be made by p arrow next, and that marks the end of our while loop. You can return count for knowing the number of elements that is in our linked list, and with that we not only complete traversal but also counting. However, I have only gone through while loop. While recursion is also an important and easy method to follow. So we are very much well aware of what recursion is. For those who do not know it very well, I'll give you a brief idea. Recursion is the process where a function calls itself. So In this case, let's say we already have our node, so we'll have to create a function because it is calling a function. So say void count, because displaying and count both can be done by a single function, and it takes a pointer. So node star p. Now we do realize that we cannot have a while loop since it is a function and it calls itself, then there would be no recursion, and thus we would have to have a different approach in this case. Firstly, I would like to recorrect a mistake I made over here. That is, it should have been struct node star p. Now what we can do next is have an if condition. If p is not equal to null, that is, it does not get up to the null pointer, we go ahead and print our value of p next, or sorry, that should have been p data. Now we go ahead and call our count function again, but this time we have p updated, that is, p is going to be p next, and that is our function right here. And this is a part of recursion where the function calls itself. So what this does is, let's see, I'll run it over here. We begin with our count with p, so that is 210. It firstly goes into the if condition. It is not true in this case. I mean, it is true, it is not a null. So we go ahead and print our data. So this prints our data, that is 8. Now we realize second case, that is, we have to give a count of next. So this is count 273. Count 273 also satisfies this condition, so it goes ahead and prints our data, that is 3. It also runs the task of the next count function, that is count 310. This realizes that it is not a null. Thus we go ahead and print the data, but now the next count is a null, and thus we end up not running the function, and function ends, exits the code, and this is what our output is. And that is how we have a linked list traversal using recursion. Now going ahead to sum of elements in a linked list, it is very much the same. That is, get a struct node the first and foremost step that we do every time, that is creating a pointer that is equal to our first. Then we have a variable named sum that it is equivalent to 0, because while traversing through the equation, the linked list, we keep updating the sum with the elements. So this is what our logic is somewhat, and the formula we are going to use. So let's begin. While p is not equal to null, we continue going now with the loop, and so sum equals sum plus p of data, p equals p next, and there goes our updation. This is how, and this is the way how we write or get the sum of the elements in the linked list. That is, this is the part where we are traversing, whereas this formula helps us get the sum. This is the updation of p to continue our traversal, and once our code ends, Now we go ahead on to finding the largest element and searching in a linked list using linear search and binary search. So going on to finding the largest element. So again this requires traversal, and we have known the first step always in traversal is having a pointer that is equivalent to our first. So that's our first step. Now we go ahead and traverse. However, first we create a variable that has a value that is going to get compared. So often we would require a small value, or it could also be the first. So there are two methods to this. Either we use min int, which is very commonly found, or we can also do int max equals first, or sorry, p data. You could use this, or we could go ahead and use this. I am going to use int min in this scenario, and thus now we traverse through the loop, the linked list. So while p is not equal to null, we compare each and every data. That is, if p of data is greater than max, then we update p data to be max. Sorry, max to be p data. I have written it the other way around initially, and I'm sorry for that. This is the right method. And now updation of p is mandatory, and thus p next, close the loop, and return max. This gives us our largest data. Let me have a quick try run. So this is our step 0 rather, that is always getting an equivalent pointer to our head of the linked list. Then we get a variable max that is having a really small value, or the first value of our linked list. Either of these work fine. We have gone ahead with having the smallest value. Then we run a loop that goes until the end, and we compare each and every value or the data stored in the node with the max variable. Anytime we find the value or the data in a single node greater than max, we equate max to that data. So say max is 3 but data is 8. Because 8 is greater, we get now max equal to 8. And we further now go ahead check with others, and if max does not ever again come again to be less than p data, we keep max as it is, and at the end we return max. This is the part where we update p to go into each and every element. Now we will go ahead with searching in a linked list. So binary search is, say this is our array. We go to the mid element, check if it is equal at mid element. If not, if the mid element is greater than the key, we go towards our left, that is the smallest edge where the possibility is, or in the contrary, if it is the mid element is less than key, we go towards right, where is the bigger. However, in a linked list, because they are not continuous data type, getting directly towards our mid element is not possible, and this binary search is not possible since it is just the traversal in a linked list, which is equivalent to the binary linear search. So beginning with our linear search, we know that in a linear search we traverse through the data set that is given in the traversal. Clearly implies that first step is going to be creation of a pointer that is going to be equivalent to our head of the linked list. And then we go ahead and okay, this is in key, say key is 12. So while p is not equal to null, that is traversal through the whole linked list until the end. If p data, that is the data in the node currently p is on, if p data is equal to key, we return p, that is the location of p, whereas or else we just say key not found. And our task is done just like that. And thus we are done with searching. We discussed why do we require, that is because we need a dynamic data set. What is a linked list? It is a collection of nodes, and thus it is dynamic. We learned how to use struct and create our user defined data type called node, which multiple collection of these nodes create our linked list. Then we learned about how several factors or several conditions such as p equals p next, q equals p, etc. work out. We learned how to traverse in a linked list, which is extremely important, and the remaining are some basic questions that we have done.